Hi, I am Neelakandan, TPGIT from Vellore. This video we are learning probability and random process, Unit 5. That is Unit 5. Unit name is linear system. The linear system definition is a system F is called linear system if f of function of a1 into x1 of t plus or minus a2 into x2 of t equal to a1 into f of x1 of t plus or minus a2 into f of x2 of t. That is called a linear system. Next one is time invariant system. That is y of t plus t naught equal to the function of x of t plus t naught. That is time invariant system. Here x of t is input function and y of t is output function. The h of omega, that is system transfer function. H of omega is system transfer function and h star of omega, that is conjugate of h of omega. H of omega equal to the Fourier transform of, that is f of h of t. The Fourier transform of h of t, that is defined by h of omega equal to minus infinity to plus infinity, the h of t into e power minus I omega t into dt. Here the conjugate function h star of omega equal to minus infinity to plus infinity h of t e power I omega t into dt. Here is e power minus I omega t. Here is conjugate function is e power plus I omega t into dt. Here small h of t is system weighting function. Now the y of t equal to h of t, the convolution, the star means convolution, h of t convolution of x of t by convolution definition. Y of t is equal to integral minus infinity to plus infinity h of u into x of t minus u into du. That is this t is change in u and the second function x of t, this t is changed t minus u into du. That is convolution definition. Next one, the stable system definition. The stable system is defined at integral minus infinity to plus infinity the modulus of h of t into dt less than infinity. Define white noise, a sample function x of t of a weights and stationary noise random process. The x of t is called weight noise if the power spectrum of n of t is a constant at all frequencies. Very important definition. Define band limited white noise. This is also very important repeated questions in 2 marks. The noise having a non-zero and constant power spectral density over a finite frequency band and zero elsewhere is called a band limited white noise. Next very important 8 mark question. 100% this question is asked in a non-exit examination. State and prove the relation between power spectral density of input and output otherwise, or this question asks another form, that is the prove that the autocorrelation function of for the density function of y, that is s yy of omega equal to s xx of omega into the modulus of h of omega the whole square, or if x of t is WSS process, that is weights and stationary, and if y of t is equal to integral minus infinity to plus infinity h of u into x of t minus u into du, then prove that the four option, that is first one is the ryy of tau equal to rxy of tau into h of tau. Second one, rxy of tau equal to rxx of tau, convolution of h of minus tau. Sxy of omega equal to sxx of omega into h star of omega. The fourth one, syy of omega equal to modulus of h omega whole square into sxx of omega. The same question asked in different ways. Proof: given y of t equal to integral minus infinity to plus infinity h of u into x of t minus u into du. That is, you want to take this equation A. First one, proof: multiply y of t minus tau on both sides in equation A. Now multiply y of t into y of t minus tau equal to integral minus infinity to plus infinity h of u into x of t minus u into y of t minus tau into du. Now take it the expectation, that is e of y of t into y of t minus tau equal to integral minus infinity to plus infinity h of u into the expectation of e of x of t minus u into y of t minus tau into du. The next step, you know that in previous unit, integral minus infinity to plus infinity, the h of u into this term, expectation of x of t minus u into y of t minus tau. This term is can be written as rxy of t minus u minus t minus tau into du. Here this minus sign multiply inside, we get this is plus t, this is minus t, cancel. Next one, this is minus u, this is minus into minus plus tau. So the integral minus infinity to plus infinity h of u into rxy into tau minus u into du. This term, expectation of y of t into y of t minus tau, this term is can be written as ryy of tau. By convolution definition, by convolution, ryy of tau equal to, this term is can be written as rxy of tau convolution h of tau. First one is proved, that is equation 1. Second one proved, multiply x of t plus tau on both sides in equation A. The x of t plus tau into y of t equal to integral minus infinity to plus infinity the h of u into x of t plus tau into x of t minus u into du. Now take this expectation on both sides, e of x of t plus tau into y of t equal to integral minus infinity to plus infinity h of u into the expectation of x of t plus tau into x of t minus u into du. integral minus infinity to plus infinity the h of u into this term is can be written as the rxx of t plus tau minus t minus u into du. Now cancel this minus t and plus t on writing that t plus tau, tau plus u, that is integral minus infinity to plus infinity h of u rxx of this t and the minus t is cancelled. Next minus into minus plus, so t plus u into du equal to integral minus infinity to plus infinity the rxx of t plus u tau plus u into h of u into du. Now put u equal to minus infinity, du equal to minus put u equal to minus alpha, comma du is equal to minus d alpha. Now integral minus infinity to plus infinity rxx of tau minus alpha the h of minus alpha into minus d alpha. This value is substituted in above integration, we get this term. Next one is take it this integral minus infinity to plus infinity rxx of tau minus alpha the h of minus alpha into d alpha. By convolution rxy of rxy equal to rxx of tau convolution h of minus tau, that is equation 2. Third one proof, consider equation 2. Now rxy of tau equal to rxx of tau into h of minus tau. Now Fourier of rxy of tau equal to the Fourier of rxx of tau convolution h of minus tau. Next, splitted this Fourier f of rxx of tau into f of h of minus tau. You know that the Fourier of rxx of tau is our spectral density function, that is S. This term is can be written as Sxx of omega into this is Fourier of h of minus tau equal to h star of omega, that is this term is can be written as this h star of omega, that is equation 3. Fourth one, ryy of tau equal to rxy of tau into h of tau. Now take this Fourier transform on both sides. Fourier of ryy of tau equal to Fourier of rxy of tau into the Fourier of h of tau equal to sxy of omega into h of omega. By equation 3 using one writing the sxx of omega into h star of omega into h of omega. So syy of omega equal to sxx of omega into modulus of h of omega the whole square. This term is can be written as sxy of omega, sxy of omega, that is equation 3. So sxy of s xy of omega, that values is sxx of omega into h star of omega. Is writing that. Next, h of omega. Here using h star of omega and h of omega, using this basic formula, z bar, that is conjugate function with function multiply, you want writing that modulus of z square. So here h star of omega, h of omega can be written as modulus of h of omega the whole square. So hence the proof. Very important result, that is note. Integral minus infinity to plus infinity e power I omega tau divided by omega square plus a square into d omega equal to pi by a into e power minus a modulus of tau. The Fourier of e power minus a into modulus of tau equal to the 2a divided by a square plus omega square. Next one, the Fourier of e power minus bt into u of t equal to 1 divided by b plus I omega. Next one, the Fourier of r yy of tau equal to s yy of omega. Next one is the inverse Fourier of s yy of omega equal to r yy of tau. Next, last one, h of omega equal to the Fourier of h of tau. Now, second problem. Consider a circuit with input voltage x of t and output voltage y of t. If x of t is a stationary process with mean 0 and autocorrelation function r xx of tau equal to e power minus 3 2 into modulus of tau, and if the system transfer function is h of omega equal to 1 divided by 1 plus I omega. Find the following. First one, the mean of y of t. Second one, the input power spectral density, that is sxx of omega. Third one, the output power spectral density, that is syy of omega. Fourth one, the autocorrelation function of the output, that is ryy of t tau. Given solution, given here, given that x of t is a stationary process with mean 0, that is e of x is equal to mu x, that is mean. Mu of x is input of mean, that is mu x equal to 0, that is given in question. Next is r xx of tau equal to 3 into e power minus 2 into modulus of tau. Next one is h of omega equal to 1 divided by 1 plus I omega. First one, to find e of y equal to mu y. You know that formula, mu y equal to mu of x into h of 0. So h of 0 values are 0. So mu x, that values are 0. You know that is given that. So mu x values are 0. So 0 into anything is anything 0. So mu y equal to 0. Second one, to find sxx of omega. The sxx of omega equal to the Fourier transform of r xx of tau. Integral minus infinity to plus infinity r xx of tau into e power, that is formula, Fourier transform of this function, that is formula e power minus I omega tau into d tau. Integral minus infinity to plus infinity, this r xx of tau function is given, that is 3 3 into e power minus 2 into modulus of tau into e power minus I omega tau into d tau. Integral minus infinity to plus infinity 3 into e power minus 2 modulus of tau into this term is e power I theta form, e power minus I theta form. So that is can be written as cos theta minus I sin theta form. So here e power minus I omega tau. So this term is can be written as cos omega tau minus I into sin omega tau into d tau. Here multiply and splitted these integrals, we get take this outside 3 in integral minus infinity to plus infinity e power minus 2 modulus of tau cos omega tau into d tau minus 3i, take this outside, integral minus infinity to plus infinity e power minus 2 into modulus of tau into sin omega tau into d tau. Here sin function is odd function, cos function is even function. So integral of odd function values are 0. So omit this integration term. Only one take this even function only, even integral only. So you want take this integral. Here even function. So cancel the modulus, and here is minus infinity to plus infinity. So 2 is multiplied, that is 3 into 2, 0 to infinity. This limit are 0 to infinity. E power minus 2 tau, modulus are cancelled because of the function is even. Okay. So cos omega tau into d tau. Since integral 0 to infinity e power minus at into cos pt equal to a by a square plus b square. Here minus a is equal to minus 2. Here omega is equal to b is equal to omega. So substitute this, we get the answer 3 2s are 6 into 2 into omega square plus 2 square. So Sx of omega is equal to 12 divided by omega square plus 4. The third one, to find Syy of omega, we know that Syy of omega is equal to, this is previous result property, Sx of omega into modulus of h of omega the whole square, that is equation 1. Given function, the h of omega is equal to 1 divided by 1 plus I omega. So take this modulus on both sides, we get the modulus of h of omega is equal to 1 divided by 1 plus I omega modulus. So inside of modulus, real and imaginary part, this term is can be written as the square root of real part square plus the imaginary part square, that is 1 square plus omega square. So the modulus of h of omega whole square, squaring on both sides, we get modulus of h of omega the whole square is equal to 1 divided by root is cancelled, so omega square plus 1. So equation 1 implies these values are substituted in equation 1, we get Syy of omega is equal to 12 divided by omega square plus 1 into omega square plus 4. Next, fourth option, to find Ryy of tau. These values are 12 divided by omega square plus 1. This values is 1 divided by omega square plus 1. This is final answer. Fourth one, to find Ryy of tau. Ryy of tau equal to inverse Fourier transform of Syy of omega. Thus formula is Ryy of tau is equal to 1 divided by 2 pi into integral minus infinity to plus infinity Syy of omega into e power I omega tau into d tau equal to 1 divided by 2 pi integral minus infinity to plus value is 12 divided by omega square plus 1 into omega square plus 4. Substitute this here into e power I omega tau into d tau. We know that this formula, basic formula, 1 divided by omega square plus alpha square into omega square plus beta square. Now splitter this denominator. So using this formula, 1 divided by beta square minus alpha square into 1 divided by omega square plus alpha square minus 1 divided by omega square plus beta square. So equal to 1 divided by 2 pi into integral minus infinity to plus infinity 12 divided by 4 minus 1 into 1 divided by omega square plus 1 minus 1 divided by omega square plus 4. Now e into e power I omega tau into d omega. Now take this constant term in outside. 12 divided by 3 into 2 pi integral minus infinity to plus infinity e power I omega tau divided by omega square plus 1 minus e power I omega tau divided by omega square plus 4 into d omega. Now splitted this integral, we get 2 divided by pi. Cancel that, we get the answer 2 divided by pi integral minus infinity to plus infinity e power I omega tau divided by omega square plus 1 into d omega minus integral minus infinity to plus infinity e power I omega tau divided by omega 2 square into d omega. Now substitute this formula, integral minus infinity to plus infinity e power I omega tau divided by omega square plus a square is equal to pi by a into e power minus a into modulus of tau. So 2 by pi into pi by 1. Here a is equal to 1, here a is equal to 2. So pi by 1 into e power minus modulus of tau minus pi by 2 into e power minus 2 into modulus of tau. So the final answer is RYY of tau equal to 2 into e power minus modulus of tau minus e power minus 2 into modulus of tau. The next question, third question, consider a weight Gaussian noise of 0 mean with R spectral density equal to n naught divided by 2 is applied to a 10 volt fast RC filter whose transfer function is h of f equal to 1 divided by 1 plus I into 2 pi f into RC. Find the autocorrelation function of output random process. Given here mean is 0 input, so mu x is equal to 0. Next one is R spectral density function. This sxx of omega equal to n naught divided by 2. The h of f is equal to 1 divided by 1 plus I into 2 pi f into RC. Omega is equal to 2 pi f. One take this. So h of omega is equal to 1 divided by 1 plus I into omega into RC. To find RYY of tau, RYY of tau equal to 1 divided by 2 pi into integral minus infinity to plus infinity SYY of omega e power minus I omega tau into d omega. To find SYY of omega, first of all you want to find out this function. omega is equal to 1 divided by 1 plus I into omega RC. Take this modulus on both sides. X modulus is denominator term is written as square root of 1 square plus omega square into R square C square. Real part square, imaginary part square. Now taking square on both sides. So modulus of h of omega the whole square is equal to 1 divided by 1 plus omega square into R square into C square. Syy of omega is equal to formula n naught divided by 2 into this modulus. This value is n naught divided by 2. This value is 1 divided by 1 plus omega square into R square into C square. That is x r y of tau is equal to 1 divided by 2 pi into integral minus infinity to plus infinity n naught divided by 2 into 1 divided by 1 plus omega square into R square C square into e power I omega tau into d omega equal to n naught divided by 4 pi integral minus infinity to plus infinity. Now e power I omega tau divided by 1 plus omega square R square C square into d omega. Now since the formula e power I omega tau divided by omega square plus a square is equal to pi by a into e power minus a into modulus of tau. This integration formula substitute we get n naught divided by 4 pi integral minus infinity to plus infinity e power I omega tau divided by R square C square. Take this outside common. We get 1 divided by R square into C square plus omega square into d omega. Now substitute this formula. N naught divided by 4 pi into R square into C square integral C minus infinity to plus infinity e power I omega tau divided by 1 divided by R square C square plus omega square into d omega. N naught divided by 4 pi into R square C square into pi divided by previous formula is using that we get pi by 1 divided by RC into e power minus 1 divided by RC into modulus of tau. Therefore Ryy of tau equal to n naught divided by n naught pi divided by 4 pi RC into e power minus 1 divided by RC into modulus of tau. The fourth question, important question, such that the sequence of x of t is a Whiteson's process, then the output of y of t is a Whiteson's. Given x of t is a Whiteson's process, then the Whiteson's process definition is x of t is Whiteson's process, then the e of x of t equal to constant and Rx of t1 t2 is equal to function of t1 minus t2. We know that this formula. Hence expectation of x of t minus u is equal to constant. So to prove that y of t is Whiteson's, so y of t is equal to integral minus infinity to plus infinity h of u into x of t minus u into du. Now take this expectation on both sides. So e of y of t is equal to integral minus infinity to plus infinity h of u into expectation of t minus u into du. So the expectation of t minus u is equal to constant. So e of y of t is equal to constant. Second condition, Ryy of t1 t2 equal to expectation of y1 of t1, y of t1 to y of t2. Now the previous formula, this formula y of t formula, integration formula, not using that, the y of t1 u t1 can be written as the expectation of integral minus infinity plus infinity h of u1 into x of t1 minus u1 into du1 u1 into h of u to r x x of t1 minus u1 minus this term is can be written as r of x x of t1 minus u1 minus t2 plus u2 into du1 du2. So minus infinity to plus infinity, minus infinity to plus infinity, h of u1 h of u2 into r x x of t1 minus t2 into minus u1 plus u2 into du1 du2. The function of t1 minus t2. Here the function of t1 minus t2 function. So second condition is also satisfied. So the y of t is Raison's process. This is first condition. Y of t is constant. So second condition is the function of t1 minus t2. Two conditions are satisfied. So y of t is WSS process. Next question. Yeah, WSS process x of t with r x x of tau is equal to a into e power minus a into modulus of tau, where a and small a real positive constants is applied to the input of a LTI systems. With h of t equal to e power minus bt into u of t, where b is a real positive constant. Find the power spectral density of the output of the system. Also find the autocorrelation function of the output y of t of the system. So solution: given r x x of tau is equal to a into e power minus a into modulus of tau, the h of tau is equal to e power minus bt into u of t. The Fourier of h of t is equal to the Fourier of, take this Fourier transform on both sides. So Fourier of e power minus bt into ut. So this Fourier of h of t is can be written as h of omega equal to, this term is can be written as in previous known result, 1 divided by b plus I omega. So to find, first one is s yy of omega, second one is r yy of tau. First one is to find s yy of omega using this result. We know that this result. So to find s xx of omega, that is s xx of omega is equal to the Fourier of r xx of tau equal to the Fourier of a into, substitute this function, a into e power minus a into modulus of tau, a into the Fourier of e power minus a into modulus of tau, s xx of omega equal to a into, this result we know that 2a divided by a square plus omega square. Next one is h of omega is equal to 1 divided by b plus I omega. Take this modulus on squaring on both sides, we get 1 divided by b square plus omega square. This is same as previous model. Now yes, yy of omega is equal to a into 2a divided by omega square plus a square into 1 divided by omega square plus b square. Substituted these values in equation 1, we get this term. Next 2a into, take this outside, 2a into 1 divided by omega square plus a square into omega square plus b square. Next step, 2a divided by b square minus a square into 1 divided by omega square plus a square minus 1 divided by omega square plus b square. Next, a divided by b square minus a square into 2a. This 2a is in multiplying inside. So 2a divided by, this denominator splitted in this form using previous result, using divided by omega square plus a square minus 2a divided by omega square plus b square equal to a divided by b square minus a square into 2a divided by omega square plus a square equal to a divided by b into b square minus a square into 2b divided by omega square plus b square. Next, to find r y of tau, that is r y of tau is